Hello, I'm Jocelyn Furtado, and in this module, I'm going to talk on the topic first order reaction. Before going to the first order reaction, we'll see what is order of a reaction. After that, we'll start with the first order reaction. And under first order reaction, we'll see the rate law expression for first order reaction, units, graph of first order reaction, half-life, examples, and at the end, we'll solve some problems. Order of a reaction. The order of a reaction can be defined as the sum of the exponents to which the concentration terms in the rate law are raised to. Consider a reaction alpha A plus beta B giving products. According to the rate law, rate is directly proportional to the molar concentration of A raised to the stoichiometric coefficient of A, alpha, into the molar concentration of B raised to the stoichiometric coefficient of B, beta. So if we remove the proportionality sign, we add a constant. Over here, we add K, which is called the rate constant. In the previous slide, we have seen that the order of a reaction is the sum of the exponents to which the concentration terms are raised to. So we can conclude that order of a reaction is equivalent to alpha plus beta. The reaction is of 0, first, second or third order accordingly as alpha plus beta, that is the order, is equal to 0, 1, 2 or 3. Suppose if the order of the reaction is 0, then the reaction is said to be of the 0th order. But if the order of the reaction is 1, then the reaction is said to be of the first order and so on. Alpha and beta are called the orders of the reaction with respect to A and B respectively. The order of a reaction is generally a small integer, but under certain conditions it can be a fraction or a zero. What is first order reaction? A reaction is said to be of the first order if the rate of the reaction depends upon one concentration term only. Consider a hypothetical case. Reactant A giving product. The rate of the reaction is directly proportional to the molar concentration of A raised to the stoichiometric coefficient of A, as we have seen earlier. Derivation for first order reaction. Consider the same reaction, reactant A giving product. Let the initial concentration of A be A moles per liter. That is the concentration which is present at the beginning before the reaction starts. After time t, if x moles per liter is decomposed or reacted, then the concentration of A after time t will be A minus x. That is, after time t, the concentration of the reactants which is remaining is A minus x. Rate is directly proportional to the molar concentration of A raised to alpha, where alpha is equal to 1 since it is a first order reaction. Substituting the value of A, that is A minus x, in the equation. Taking the derivative of rate, we get dx upon dt is directly proportional to A minus x. By removing the proportionality sign, we add a constant k, where k is called a rate constant or specific reaction rate. Let's number this equation as equation number 1. In the next slide, we are going to rearrange this equation and bring all the x terms on one side. After rearranging the equation 1, we get dx upon A minus x is equal to k dt. Integrating the above equation, we get this. K is a constant, so it is written outside the integral sign. By using the formula in the box in this equation, we get minus ln A minus x is equal to kt plus I, where I is the constant of integration. Let's number this equation as equation number 2. To find the constant of integration I, we put the initial conditions, that is t is equal to 0 and x is equal to 0. Substituting these initial conditions in equation 2, we get, after solving the equation, we get I is equal to minus ln A. Substituting the value of I in equation 2, we get minus ln A minus x is equal to kt plus I. Instead of I, we put minus ln A. By using the formula in the box, we get kt is equal to ln A upon A minus x. Since we want to find the equation for rate constant k, we take the t on the other side. To convert ln into log, we multiply the equation with 2.303. After multiplying, we get the value of k as 2.303 upon t log of A upon A minus x. This is called the rate law expression for first order reaction. Now we are going to see the units of first order reaction. We consider the rate law expression for the first order reaction and substitute the units of each of the components. Since 2.303 is a constant, we put the unit as 1. Instead of t, we substitute the units of t. The units of time can be seconds, minute, hour, day, month or year, etc. Into the units of A, that is moles per liter, upon the units of A minus x, that is also moles per liter. The moles per liter and moles per liter will get cancelled, and finally we will get the unit of K as time inverse. Therefore, we can say that the unit of K will be second inverse, minute inverse, hour inverse, etc. Graph of first order reaction. We take the rate law expression and rearrange the equation as follows. Now the reaction is of the type y is equal to mx plus c, where m is the slope of the reaction. If we compare the two equations, we see that m is equal to minus k upon 2.303. If we remove the slope from the graph, that is m is equal to y2 minus y1 upon x2 minus x1, then we get a negative slope since the concentration of the reactants decreases. If we equate this negative slope with minus k upon 2.303, then we get the value of k as 2.303 into the slope. Now let us see the half-life of first order reaction. The time in which the concentration of a reactant is reduced to half of its original value, that is 50% of its original value, is called half-life period of the reaction. Derivation of half-life for first order reaction. Starting with the rate law expression. When half of the reaction is completed, the value of x, that is the amount of reactants that are decomposed, is equal to half of the initial concentration of the reactants. And time is equal to t half. Substituting these values of x and t in the above equation, we get. Now we are going to solve the log part, and after solving it, we get this. The a and a on the right hand side gets cancelled and we get log of 2. Since we are finding the expression for t half, we will keep the t half on one side and take all the other terms on the other side. Substituting the value of log 2 in the equation, we get, after solving the equation, we get the value for t half as t half is equivalent to 0.693 upon k. This is the equation for half-life of first order reaction. Let's look at some examples of first order reaction. First example, hydrolysis of ethyl acetate in acidic medium. We take ethyl acetate and hydrolyze it in acidic medium and we get acetic acid and ethanol. The second example is inversion of cane sugar. Glucose is dextrorotatory while the products formed, that is glucose and fructose, are dextrorotatory and levorotatory respectively. Also, the lever rotation of fructose is more than the dextro rotation of glucose. On hydrolysis, as you can see in the equation, the dextro-rotatory sucrose gradually changes into a levo-rotatory mixture. It is for this reason that the reaction is called inversion of sucrose. Now let us solve some problems. A first order reaction is 40% complete at the end of 50 minutes. What is the value of the rate constant in second inverse? Find its half-life. Whenever the concentrations are in percentage, the initial concentration is always taken as 100. In the question, it is mentioned that the reaction is 40% complete. That is, 40% of the reaction has been decomposed. Therefore, the value of x is 40. To find a minus x, we substitute the values of a and x and we get the value of a minus x as 60. In the problem, it is said that 40% reaction is complete at the end of 50 minutes. So, the time is 50 minutes. But they have asked us to find the rate constant in second inverse. So, we'll have to convert the minutes into seconds. To convert the minutes into second, we multiply 50 into 60. After multiplying, we get the value of t as 3 into 10 raised to 3. After substituting the given values in the rate law expression, we get the answer as 1.703 into 10 raised to minus 4 second inverse. This is the value of K. But in the question, they have asked us to find the half-life of the reaction. So we'll have to substitute the value of K which we have found out in the equation of T half. T half is equal to 0.693 upon K. Substitute the values and we get the answer as 4.069 into 10 raised to 3 seconds. Problem 2. A radio element has half-life of 82 seconds. Calculate the time taken by the radio element to reduce to 15% of its original activity. For radio elements, instead of K, we write lambda. Substituting the value of T half in the equation, we get the value of lambda as 0.008451 second inverse. To calculate the time taken, we consider the rate law equation where N0 is the initial concentration which we will take as 100% and N is the remaining concentration, that is 15% as said in the problem. That it reduces to, that is the remaining concentration is 15%. After rearranging the equation and substituting the values in the equation, we get the value of T as 224.5 seconds. Problem 3. Decomposition of hydrogen peroxide follows first order kinetics with the specific reaction rate being 6 into 10 raised to minus 4 second inverse at 303 Kelvin. Calculate the concentration of hydrogen peroxide after 10 minutes if we start with 0.05 mole per dm cube initially. In the problem, they have given the value of K as 6 into 10 raised to minus 4 second inverse and time they have given in minutes. So, we have to convert it into seconds as we have done in the previous problems. So, 10 into 60 gives us 600 seconds. A is given, that is the initial concentration is 0.05 moles per dm cube and they have asked us to find X, that is the amount of reactants that have been decomposed. Rearranging the rate law expression, we get this. After substituting the given values on the right hand side, we get 0.1563. We take the log from the left hand side to the right hand side and when we do this, the log is converted into an anti-log. After solving, we get A upon A minus X is equal to 1.462. Substituting the value of A, that is 0.05 in the equation, we get this. And after solving it, we get the value of A minus X as 0.034. We take the a on the other side and we get x is equal to 0.034 minus a. Substitute the value of a in the equation and we get the value of x as 0.016 moles per dm cube. Now we are going to see some MCQ problems. The reaction rate is defined as the rate at which the concentration of the reactants dash with time or the concentration of products dash with time. The options are as follows. As the reaction progresses, the reactants will react and get converted into products, hence decreasing the concentration of the reactants and increasing the concentration of the products. So answer will be this. Problem 5. For the first order reaction, rate constant K is given by Kt is equal to log C0 minus log Ct, where C0 is the initial concentration and Ct is the concentration at time t. Graph between log Ct and time t is. So here we have to identify the graph of first order reaction. As we have seen earlier in the previous slides, the graph of first order reaction is a straight line with a negative slope. And if we compare the given equation by y is equal to mc, we get the answer as B. These are the references used in this module. Thank you.